Welcome to Acids and Bases. In today's lesson, we are going to focus on the theory portion of the unit Acids and Bases. First, you need to know an operational definition. An operational definition is also known as an empirical definition. An operational definition is based on operations or experiments that can be performed in the lab. That is, operational definitions come from observations made in a laboratory setting, whether that's what you see, what you taste, what you touch. It can be confirmed with the naked eye. Operational definitions can be used to classify substances, but they cannot be used to predict chemical formulas or explain why it acts the way that it does. You were introduced to operational definitions in junior high. It is important that you recognize the operational definitions of acids and bases. These are usually asked as a multiple choice question. For acids, they taste sour, they turn blue litmus paper red, they conduct electricity, they have a pH of less than 7, they react with protons, and they react with active metals to produce hydrogen gas. This is a very popular one that you may not have been introduced to before. And of course, acids will neutralize a base. Some common everyday examples of acids are lemons, yogurt, and vinegar. Bases, on the other hand, taste bitter, turn red litmus paper blue. They also conduct electricity but have a pH of greater than 7. They feel slippery to the touch and they neutralize an acid. Some common everyday examples would be baking soda, oven cleaner, and antacids. A conceptual or theoretical definition explains why something has certain properties. In Chemistry 3202, we will study 3 different types of theoretical definitions. In the IB portion, we'll be introduced to a 4th. The first theoretical definition of acids and bases was the Arrhenius theory. According to the Arrhenius theory, acids are any compound or species that dissociate to yield hydrogen ions. That is, it is a compound that will strictly break apart into its 2 component ions, one of which would be H positive. Let's look at 3 examples. If we were to take HBr and break it up into its component ions, we would get H positive, excuse my writing with my finger, plus Br negative. As you can tell, when it was broken apart, we obtained the H positive ion. Therefore, we can predict, according to the Arrhenius theory, HBr has acidic properties. Looking at HCl now, this can break apart into H positive and Cl negative. Again, we have obtained the H positive ion, therefore we can predict that HCl has acidic properties. Lastly, looking at HNO3, this would break apart into H positive and NO3 negative. Obtaining the H positive ion, we can predict that HNO3 has acidic properties. According to the Arrhenius theory, a base is any species that dissociates to yield the hydroxide ions, also known as OH-, in aqueous solutions. That means, by looking at the examples, if we break the compound into its component ions, it should yield OH-. Let us first look at sodium hydroxide, NaOH. If we were to break this up into its 2 ions, the cation and the anion, we would get Na positive and OH-. Since we have obtained the OH- ion, we can safely predict that according to the original Arrhenius theory, sodium hydroxide would be a base. I would like to note at this time that for any sort of assessment, including the public exam, it would be expected that states of matter, meaning aqueous, would be provided in your answer. Let us now look at potassium hydroxide, KOH. At this point, you should be able to easily look at this compound and know that it will break up and give you an OH- ion. To confirm, we get K positive and OH-. With lithium hydroxide, we get Li positive and again OH-. You should get in the practice of looking at a compound and being able to predict if it is an Arrhenius acid or base simply by looking at it. The original Arrhenius theory is the first known theory that we have been discussing. The Arrhenius definitions of acids and bases are theoretical because they explain acidity and alkalinity in terms of the species responsible for those conditions. They are not operational, as we discussed on the last page, because we cannot actually observe this with the naked eye. The original Arrhenius theory, while it did pave the way for acids and bases, is not perfect or foolproof. There are some limitations of the Arrhenius theory that you should be aware of. For example, not all compounds that contain hydrogen are automatically acidic. Not all of the hydrogens are ionizable. For example, in CH3COOH, or acetic acid, only the H at the end is actually ionizable. The more famous limitation of the original Arrhenius theory is the fact that not all bases will produce hydroxide in actual life. The most popular example being ammonia, which is NH3. We know based on the observational definition of ammonia that it is a base. However, using the Arrhenius theory, we would not successfully predict that it is a base. This brings us to the modified Arrhenius theory. The modified Arrhenius theory introduced the idea of the hydronium ion, H3O positive, to replace H positive in our theoretical workings. According to the modified Arrhenius theory, an acid is any species which forms an acidic solution in water to increase the H3O positive concentration. Some important components of this definition include the fact that in order to predict something as being an acid, it has to react in water. Not only does it have to react in water, it has to produce the H3O positive ion, as you can tell in the example of HBr. HBr is an acid according to the original Arrhenius theory, and now we can successfully predict the same using the modified Arrhenius theory. According to the modified Arrhenius theory, a base is any species that again dissolves in water, this time to increase the hydroxide ion concentration. By modifying the original Arrhenius theory to include that the example has to be dissolved in water, we have now taken care of the original limitation of not being able to predict ammonia as being a base. As you can see in this example, when ammonia reacts with water, it does in fact produce OH-, and now we have successfully predicted ammonia as being a base. However, the modified Arrhenius theory is not without its own limitations. For instance, as you can tell based on the examples above, you are restricted to aqueous solutions, meaning you have to take each compound in question and react it with water and only water. Another limitation of the modified Arrhenius theory is the fact that it does not help predict whether a substance will be an acid or a base if it can act both as an acid and a base. This is a concept that we will discuss in further pages. This now brings us to the Bronsted-Lowry theory, which is commonly called the proton transfer theory. For the remainder of the chapter in Chemistry 3202, we will be using the Bronsted-Lowry theory to write out acid and base reactions for calculation-style problems. The Bronsted-Lowry theory is an acid-base reaction that involves the transfer of a proton. Recall from Science 1206 that a proton has a positive charge. In the acids and bases chapter, we will represent a proton as H positive. According to the Bronsted-Lowry theory, an acid is any chemical species that loses or donates a proton in a chemical reaction. Recall from previous examples that we have confirmed that HBr is in fact an acid. Notice that it does have a proton or an H positive ion that it can donate. According to the Bronsted-Lowry theory, a base is any chemical species that gains or accepts a proton in a chemical reaction. Again, recall from previous examples that we have identified OH- as being a base. Notice that the OH- ion has an overall negative charge. This means that there is room in an OH- ion to accept a proton or an H positive charge. This brings us to the concept of conjugate acid-base pairs. Conjugate acid-base pairs are two species that are related by the transfer of a proton. That is, conjugate acid-base pairs are any two species who differ only by an H positive charge. Every acid-base reaction has two pairs. Let us look at the example of acetic acid reacting with water. First, we look at the reactants to identify the Bronsted-Lowry acid and the Bronsted-Lowry base. Looking ahead at the products, you should be able to easily identify which reactant had to give away a hydrogen to produce the product and which reactant had to accept a hydrogen to make the product. You can see on the products that acetic acid must have gave away the hydrogen at the end in order to produce the acetate ion. I'll show that with an arrow pointing towards the water. You should also be able to see that water gained the hydrogen in order to make the hydronium ion. So again, acetic acid in this case was the acid since it gave away the hydrogen, and water is the base since it accepted the hydrogen. This is all according to the Bronsted-Lowry definitions. Now, looking at the products, we have the hydronium ion and CH3COOH. If we were to reproduce the reactants, you should then see that the hydronium ion would have to give away the hydrogen to the CH3COO ion in order to reproduce acetic acid. Therefore, H3O positive on the product side is acting as the acid. To clarify that this is the acid on the product side, we will write this as the conjugate acid, and then the conjugate base. On an exam, when they ask you to identify the conjugate acid-base pairs, you must also write them on the bottom paired up. CH3COOH gets paired with CH3COO negative as they differ only by an H positive ion, and H2O is paired with H3O positive because again they differ only by a hydrogen and a positive charge. Notice here that water has 2 hydrogens and the hydronium ion has 3. Water has no charge. H3O positive has a 1+ charge. So again they differ only by an H positive. It is important that you know the definition of amphoteric and also know that it is sometimes referred to as amphiprotic. Amphoteric substance is any substance that can act like a base in one reaction and an acid in another reaction, meaning it can accept a proton in some cases and donate a proton in others. Let us look at the example of HSO4 negative. HSO4 negative is an amphoteric substance. Let us look at the first line. In this case, HSO4 negative is reacting with HOOCCOO negative. Looking ahead at the products, it should be easy to see that HSO4 negative must give away its hydrogen in order to produce SO4 negative. In this case, HSO4, since it is donating a proton, is acting as the acid. Let us look at the next line. In this one, looking ahead at the products, you should be able to see that the hydronium ion must give HSO4 negative one of its protons in order to produce H2SO4. You can see that HSO4 negative is increasing by an H and a positive. In this case, since HSO4 negative is accepting a proton, it is acting as a base. By doing this, we have proven that HSO4 negative is an amphiprotic substance. All amphiprotic substances must have an H in the front to donate and an overall negative charge in order to be amphiprotic. This is because in order to be an acid, it has to have a hydrogen to give away, and to be a base, it must have an overall negative charge in order to accept an H positive. The only exception to this rule is water. Water is also amphiprotic, which we will discuss in a later lesson. You are also responsible for being aware of the 6 strong acids and how they work. Know that a strong acid is an acid that ionizes completely in water, meaning 100% of the reactant is converted to its component product. The 6 strong acids are HCl, or hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodoic acid, HClO4, perchloric acid, HNO3, nitric acid, and H2SO4, sulfuric acid. For Chemistry 3202, these 6 strong acids are the first 6 listed in the acids and bases strengths table. Weak acids, on the other hand, are any acids that ionize partially in water. That would be any acid other than the 6 strong acids. A weak acid, when added to water, does not completely react, usually less than 50% for most acids that are weak, and therefore it does not produce the stoichiometric equivalent amount of the hydronium ion, meaning we cannot use simple stoichiometry to predict the amount of product that will be produced, as we do not know the extent of how much is actually converted to being a product. For example, acetic acid, when reacted with water, only reacts with a 1.3% reaction. That means that for every 1,000 particles of acetic acid, only 13 actually react. Strong bases are any base that dissociates completely when dissolved in water to produce the stoichiometric equivalent of the hydroxide ion, just as strong acids ionize completely when dissolved in water to produce stoichiometric equivalent amounts of the hydronium ion. The strong bases, while not explicitly stated on the acids and bases strengths table, are any compound that contains the OH- ion. NaOH, KOH, LiOH, BaOH2, SrOH2. It must have the hydroxide ion present to be a strong base. Weak bases are any base that does not completely ionize in water, so it doesn't produce stoichiometric equivalent amounts of the hydroxide ion. For instance, ammonia, NH3, obviously does not contain hydroxide or OH-. Therefore, it's easy to predict that this will be a weak base. In fact, it only reacts with a 0.12% reaction. Since weak acids and weak bases do not ionize or dissociate out completely, we cannot use simple stoichiometry to predict the amount of product produced, and therefore we must resort back to our old ICE table. Don't worry, that's coming soon. Next, we're going to look at predicting Bronsted-Lowry acid-base reactions. I want you to put a star next to this topic as it is extremely popular on the public exam. To best explain how to proceed with predicting Bronsted-Lowry acid-base reactions, we're going to work through an example together. In this example, we are going to determine the acid-base neutralization that occurs between aqueous solutions of sodium hydrogen sulfate, NaHSO4, and ammonium bicarbonate, NH4HCO3. These reactants are given here. The first step in determining a Bronsted-Lowry acid-base reaction is to write all species as they exist in aqueous environment. Recall from Science 1206 that ionic compounds, that is, any compound that contains a metal and a nonmetal, such as sodium hydrogen sulfate, so this is ionic, or anything that contains the ammonium ion, such as ammonium bicarbonate. There you go. In aqueous environment will dissociate out into their component ions. So in step 1, when we need to write all species as they exist in aqueous environment, instead of writing NaHSO4, we are going to write the fact that in aqueous environment, this ionic compound will dissociate, and it actually contains Na positive, aqueous, and HSO4 negative, aqueous. Likewise, for ammonium bicarbonate, that also dissociates out in aqueous environment, so we have an H4 positive, and HCO3 negative. And lastly, even though it's not explicitly stated in this question, notice that both of them are in fact in aqueous environments. And an aqueous environment simply means that the compound has dissolved in water. Therefore, we also need to include water in our list of compounds or species that are present. In step number 2, we now need to identify all possible acids and bases according to the Bronsted-Lowry definition. Recall that the Bronsted-Lowry definition states that acids are proton donors and bases are proton acceptors. So, I'm going to write all of our species in a list again. So we have Na positive, HSO4 negative, NH4 positive, HCO3 negative, and H2O liquid. Now we need to classify each of these. Recall from Science 1206 that sodium, Na, is simply a metal. Metals contain no acidic or basic properties, so we're going to forget about that altogether. HSO4 negative. Notice that this has a hydrogen in the front and an overall negative charge, which are the two things that we need in order for something to be amphoteric, meaning this can be an acid or a base. Then we have NH4 positive. Notice that this has an overall positive charge as well as multiple hydrogens, meaning that this can act as an acid. We have HCO3 negative. So again, we have a hydrogen in the front and an overall negative charge, meaning this can be an acid or a base. And we have water. And recall from our lesson on amphoteric species, that is the one exception to the rule, and water can also be an acid or a base. Okay, so step number 2, after you've written all of the species in the environment, you have to then identify if they are an acid or a base or both or neither, such as Na positive. In order to continue, With the example on predicting a Bronsted-Lowry acid-base reaction, you now need to take out your acids and bases strengths table. This is located in your data booklet. Step number 3 is to now identify the strongest acid from the list that you've made in step number 2. Recall from step number 2 that the possible acids include HSO4 negative. We identified NH4 positive as possibly being an acid, HCO3 as possibly being an acid, and water. In order to determine the one that's actually going to act as the acid, we need to identify the strongest, and this is where the acids and bases strengths table comes from. What you now need to do is you need to find all 4 of these on your acids and bases strengths table. The acids and bases strengths table is set up so that the strongest acids are listed first, and they go down through the list to the weakest acid. As stated for step number 3, we now need to find the 4 possible acids on the acids and bases strengths table. I can right away see at the bottom that I have water, and remember that the acids and bases strengths table is set up so that the weakest acid is on the bottom and the strongest is at the top. I also see HCO3 negative, NH4 positive, and up here, HSO4 negative. Recall that we need to find the strongest acid, and since HSO4 negative is at the top, this one is the strongest out of the 4. So we'll write that now in step 3. Again, from our work on the acids and bases strengths table, we have identified the strongest acid as being HSO4 negative. Now we have to do the exact same thing to identify the strongest base. Recall that some of the bases are HSO4 negative, which we can automatically get rid of because we now know that's actually acting as the acid, and we have HCO3 negative, and we have water. Since we do have 2 possibilities, we now need to go to our acids and bases strengths table to find the strongest base. Please note that the acids and bases strengths table is set up so that the weakest base is at the top and the strongest base is at the bottom. This is the opposite of how it's set up for the acids. Again, we need to find in this list all of the possible bases. I see water here at the top, as well as HCO3 negative here. Recall that bases increase in strengths towards the bottom, so the strongest bases are at the bottom, whereas acids increase in strength the opposite way. Since HCO3 negative is closer to the bottom than water, we've now identified HCO3 negative as being the base. From the work with the acids and bases strengths table, we have now identified HCO3 negative as being the strongest base. Notice here that I'm using the terminology strongest base and strongest acid, not strong acid and strong base. Recall from our work earlier in this lesson that HCO3 negative is not one of the 6 strong acids, nor is it a strong base, but it is stronger or the strongest from the list. Once you've identified the strongest acid and the strongest base, we now need to write those as the reactants. So again, I have HSO4 negative and HCO3 negative. For now, I'm going to forget about the arrows and just predict what the products are going to be. Recall that HSO4 negative is our acid, HCO3 negative is our base, so the HSO4 is going to donate an H positive or a proton to HCO3. That would leave us with just SO4 since the hydrogen is gone. It originally had an overall negative charge, and now it's lost another positive, leaving us with SO4 2 negative, aqueous. HCO3 negative gained a hydrogen, so now I have H2CO3. It did have an overall negative charge, but now it's gained a positive. And remember that a negative and a positive makes overall neutral, so I won't write anything there. In order to ensure that you have the charges written correctly, the charges on the reactant side, here being 1, 2 negative, should equal that on the product side, 2 negative. Lastly, in order to ensure this question is correct, we now need to determine what type of arrow we are going to use. Recall from the beginning of the year, we've been introduced not only to a single-headed arrow, but we've also been introduced to an equilibrium arrow. Here is the criteria that you use. If there is a strong acid, so one of the 6 strong acids present, we use a single-headed arrow. If there is a strong base present, meaning hydroxide is present, then we use a single arrow. However, if both the reactants are a weak acid and a weak base, then we need to use the equilibrium arrow. HSO4 negative is not one of the 6 strong acids, and HCO3 negative does not contain hydroxide, so it's not a strong base. Therefore, we need to use an equilibrium arrow here. So our final answer would be HSO4 negative, aqueous, plus HCO3 negative, aqueous, equilibrium arrow, SO4 2 negative, and H2CO3, or carbonic acid. Let's put this all together now and try one last example. Write the Bronsted-Lowry acid-base reaction between sodium hydrogen sulfate and potassium carbonate. You will have to recall the rules of naming from Science 1206, as well as use your periodic table, in order to write the formulas for sodium hydrogen sulfate and potassium carbonate. Sodium hydrogen sulfate is NaHSO4. Since sodium has a 1 positive charge and hydrogen sulfate from the back of the periodic table has an overall negative charge. And potassium carbonate, which would be K2CO3. Since potassium has a positive charge and then carbonate has an overall 2 negative charge. If you require extra help with that, please let me know. Step number 1 is to write the species as they exist in aqueous environment. Notice that sodium hydrogen sulfate contains a metal and a nonmetal, and potassium carbonate also contains a metal and a nonmetal. This means that these two compounds are ionic and in aqueous environment will break into their component ions. So we actually have Na positive, HSO4 negative again, K positive, and CO3 2 negative. And remember, for every example where we predict Bronsted-Lowry acid-base reactions, since they're taking place in aqueous environment, we also need to consider the presence of water. Next, we need to label if they are acids or bases. Recognize that we just identified sodium as being a metal, as well as potassium as being a metal. Since metals have no acidic or basic properties, we can automatically take these out of the race. HSO4 negative is amphoteric, so it can be an acid or a base. Carbonate has no hydrogen at all, so it's impossible for it to be an acid, but it can be a base since it has a 2 negative charge. It can accept not 1, but 2 protons. And water is, of course, amphoteric. Now you need to go to your acids and bases strengths table to determine which one is a stronger acid, HSO4 negative or water. When you look, you should notice that HSO4 negative is the stronger of the two. Likewise, you now need to go to determine if CO3 2 negative or H2O, water, would be the base. When you do, you should realize that CO3 negative is a stronger base than water. We can now take these two and write them out for the Bronsted-Lowry acid-base reaction. HSO4 negative aqueous plus CO3 negative aqueous. Notice that neither of these are strong, so we'll use an equilibrium arrow. HSO4 negative has been described as the acid, so that will be the one giving away the proton. This will leave us with SO4 and an overall 2 negative charge now, since it's lost a positive, and HCO3. It originally had a 2 negative charge and it's gained a positive, so this now has an overall negative charge. Again, recall that you should check your reactants and your products to make sure the overall charge of the reactants, in this case 3 negative, is the same as the products, in this case 3 negative. Charges are the most common mistake made by students in this type of question. At this point, you now have all of the tools to complete this worksheet. Please try your best and then check your answers with the file that's already been posted. Thanks so much.